Hello, my name is Halbach Romero Calvo, and I am a PhD student at the University of Colorado Boulder. I would like to welcome you all to this presentation on behalf of my co-authors, where we are going to introduce our new concept of operation of electrolytic cells in zero gravity. As you probably know, by electrolysis we mean the electrochemical decomposition of water into hydrogen and oxygen. There are two main technologies related to electrolytic cells. The first one is alkaline electrolysis, where we dissolve sodium hydroxide or potassium hydroxide in water, liberating the hydroxyl groups and generating a conduction loop between two electrodes by means of a porous membrane. Or we have proton exchange membranes, where the role of the hydroxyl is actually played by protons in the membrane. Normally, proton exchange membranes are preferred for space applications because the membrane prevents the instantaneous and exothermic recombination of hydrogen and oxygen into water, and then it is safer for space applications. There are three main ways to operate a proton exchange membrane. These are liquid anode, liquid cathode, and a static water feed. The main disadvantages, these technologies have different advantages and disadvantages, but the disadvantages are mostly related with the water content of the resulting gases and the need for phase separators. This is particularly true for low gravity application. Let's see why. If you operate an electrolytic cell in zero gravity, you will soon see that a layer of gas bubbles is created over the electrode, and this reduces the effective surface area of such electrode. Of course, you need a way to remove these bubbles and then separate the water and gas flow in microgravity. As you know, in microgravity, you don't have a buoyancy force as we do on Earth. So we need to apply something else, and that something else is phase separators. However, phase separators account for a significant mass and power budget of our system, as we can see, for instance, in the oxygen generation assembly of the International Space Station. There are two main phase separation technologies currently employed. The first ones are membranes. Membranes are unpowered, but they have a limited lifetime because the membrane degrades. We also have rotary devices, but rotary devices require a power input, and they actually induce a significant disturbance, acceleration disturbance to our spacecraft. Some alternative concepts, maybe for instance the spacecraft spin, which is basically the same as a rotary device, where the rotary device is a spacecraft itself, and this was proposed for Doyle and Peck for the pair of CubeSats. And you also can use conduit geometries that make use of the inherent surface tension properties of the water-gas interface to perform a natural phase separation, as proposed by Jensen and in this wonderful paper that I surely recommend. Our concept is different from all those, and is based on the utilization of the diamagnetic properties of water and associated electrolytes. So water is a diamagnetic. This means that water is repelled from magnets. But this, on the other side, generates an artificial magnetic buoyancy force that makes the gas bubbles in water being attracted towards the magnet, as you can see in this illustration concept figure that we have placed. If the water or if the liquid that we were employing was paramagnetic or ferromagnetic, such as a ferrofluid, it will feel attracted towards the magnet, and the configuration will have to be inverted, as you can see here. However, space systems aim at modularity. Indeed, we can use the same principle, magnetic buoyancy, to induce phase separation in low gravity environments, as you can see here. This concept can be implemented by itself, standalone, or can be combined with alternative approaches, such as the conduit geometry's natural approach. And this may help solve actually some of the problems that this system presents when a very small bubble gets into them and does not touch the walls of your conduit geometry container. So this is the idea. Magnetic fields can be used to separate the gas bubbles from the electrodes, to pull the gas bubbles from the electrodes, or to induce phase separation in a separate module. The theoretical framework behind this idea is pretty complex. We describe it extensively in our paper, but the idea is that for low susceptibility liquids, such as water or associated electrolytes, you can decouple the fluid magnetic problem into two separate modules and compute the magnetic field beforehand, and then apply it to your fluid mechanics problem. In terms of when we think about the electrodes, the magnetic field influences the growth, detachment, and displacement of the bubbles. And we are going to consider these three equations: magnetic Fritz equation that determines or estimates the bubble detachment diameters, the effective total force exerted by the magnetic field in the bubble, and the terminal velocity that the bubble reaches in water. It is worth noting that liquid electrolytes present actually higher susceptibilities of the order of 50% higher than water. So let's explore a bit, let's get a taste of this concept. We are using a 1 millimeter radius oxygen bubble at 25 degrees and 1 atmosphere. And we are considering a magnet with this residual magnetic flux density, which is one of the strongest in the market currently available in microgravity conditions. So in the plots, you will see the magnetic field lines as dashed lines, and the magnitude that we're representing, in this case, the volume force, as constant contour lines and force vectors. So we can see that the magnetic field is able to generate a magnetic force of the order of 1 nanonewton per millimeter cube, which is 1 newton per meter cube, which for the case of the oxygen bubble is more or less 1 meter per second square of acceleration. This is huge in the microgravity environment. However, we have to be careful because, as I said before, what really matters is the terminal velocity that gives us the steady state velocity of the bubbles in our system. These steady state velocity maps are represented in these three plots for different magnets with different shapes. We can see that the 1 millimeter per second steady state velocity is always between 1 and 2 centimeters from the surface of the magnet. We can play around with this with the magnet configuration to optimize our system and to improve our design. However, we can also modify the magnetization vectors to adopt different configurations. So, for instance, in this 2D simulation, we can see the uniform magnetization. We can see that the bubbles tend to be collected at the streams of the magnet. This may be convenient for phase separators. It is not convenient for electrolytic cells itself when we apply the magnet to the electrolytic cell, because then we don't generate an uniform force distribution on the surface of the electrode. On the contrary, Halbach arrays, which are pretty popular in biomedical applications, can generate a more uniform force and then velocity distribution, and can be employed in a space system by simply tuning the magnetization vectors of our system. In terms of bubble break-off diameter, we compute the Fritz equation and the magnetic Fritz equation. We can see that the magnetic field actually has a strong influence in the system. However, these curves have to be analyzed with care or read with care, because we're actually violating the assumptions of the system. First of all, the force is not uniform as in the Fritz equation, as the Fritz equation assumes. And then when pool boiling or pool electrolysis is performed in the surface of the electrodes, we actually have several bubbles colliding together. So we cannot study this problem as if it was only a single bubble. In other words, we need more complex numerical simulations to actually understand what is the specific effect of the magnetic field in the system. Complex simulations or experiments in microgravity. It is worth noting that, as I said before, the liquid electrolytes present better performances than pure water. So to conclude this presentation, the phase separation state accounts for significant mass and power penalties in low gravity technology applications, like electrolytic cells, because of the absence of buoyancy force. However, we can use the inherent magnetic properties of water and its associated electrolytes to induce a magnetic buoyancy force that helps us overcome these difficulties. Halbach arrays and other smart magnetic configurations can be employed to optimize our systems, but further CFD simulations, numerical simulations, or experiments need to be carried out to understand some of the fundamental aspects of this concept of operation of electrolytic cells. That was all for today. Thank you so much for your attention. And if you need further details, feel free to read our paper where we describe the theoretical framework extensively, or reach out by any of the means that you can see in this slide. Thank you again for your attendance.